Let's have some more fun and check out the ghosts of gravity from 280 BC to 1784 CE. So these ghosts are going to be more people who have tried to figure out what gravity was and just failed, I suppose. They had their hypotheses, they got close, but they still couldn't do it. These are nearly accurate theories. So the math was somewhat advanced, but at least more advanced than previous math, but the physics was still incomplete. It starts off with Archimedes from Syracuse. So he figured out that you can have equal weights at equal distances in equilibrium. Basically the center of mass idea. So we started drawing different geometric drawings like this, and figured out that there's a point over here that gives you the center of mass if this was equally massed, the equal density. He also figured out Archimedes' principle of buoyancy. So, you could have an object right here, and depending on how much it is submerged and the ratio of the density to the fluid, you can essentially calculate the buoyant force. Now, he didn't really do any math, so there was no algebra here. So that's why I didn't write the equation that we know today, because he was doing this all with geometry. And you can see kind of how that might have appeared back in the day when he was sort of thinking about these things and how he might have drawn these geometric figures and principles. So that was Archimedes from Syracuse. A little later, in fact, this was 150 CE, so after Christ, versus Archimedes was before Christ. Now we're after Christ in the Common Era, and we have Claudius Ptolemy, this guy right here, and he wrote the standard model of astronomy from back then, the Almagest, 13 books full. And he found that the Earth was actually motionless, or he thought that the Earth was motionless at the center of the solar system. He thought about this in terms of rotating spheres or rotating circles, and then these little epicycles where they kind of twist around in their axis, uh, in their little rotational circles here. So these little epicycles. And this is pretty good at predicting the planetary positions. He called them large circular definite orbits with small epicycle corrections. And he had to do this, though, with trigonometry, ratios, and geometry. Still no algebra, still no math here. And this was Claudius Ptolemy. We get into Leonardo Fibonacci. We might know this guy. I mean, maybe not by vision, but we know his sequence. Everyone should know the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21. We like to use these to like trade in the stock market, like figure out patterns and these little fractals and stuff. So here's the spiral. You can see it's like 1, 1. Efficient arithmetic by use of the numerics, real numerals. So before they were doing those weird Roman numerals or Greek numerals or Hindu numerals, and they used very strange symbols. But now we've got these actual symbols that we almost use today. So we have like a 1, we have a 2, we have a 3, we have something that looks similar to a 4, but not really. We have something that's like a 5 here, and then 6. You just kind of get a little messy here. It's a backwards 9. And then here's 0 for 0. So he was able to bring these numbers, and he wrote this Liber Abaci book. So that's what replaced the Roman numerals of the time, and he sort of came up with this new sequence because he was studying the numbers. That's why he came up with this sequence here. He got good at numbers. But still, no equations, basically just descriptions. A square and 10 roots is equal to 39 would be something that he would write. This was Leonardo Fibonacci in 1200. We got a little bit later, we got 1250 when Jordanus de Nemore. This guy pops up and he's like, all right, let's just start using symbols now. So he has syncopated algebra. A little bit of symbols. You got like R is the root, R squared is the square, R third is the cube, and you can kind of see how that might have been written out here. I'm not sure if this was exactly his particular writings, but this would be something that would be written in syncopated algebra, where you kind of have like a little bit of symbolism and then mostly words, like words and symbols combined. That was syncopated algebra, back and forth between words and numbers and symbols. So R squared 10R, 39, where equals. This is Jordanus de Nemore's little models here. So some of the earliest algebra that was ever finally created. Abbreviated notation, we can say. And this was Jordanus de Nemore. A few hundred years later, we get to Nicolaus Copernicus. This guy's pretty important because um, he was the first person to realize that the sun is at the center of the solar system. So this was his model right here. We have the sun and we have the planets sort of going like this. This might be Earth, Tilares, Terrares, pardon. Can't really see this. Venus and Mercury and Martes. I think that's Jovis and Saturn. Anyway, so he figured out that the Earth rotations, they have three types of rotations. You have the daily rotation where it's spinning around. This is the little arrow right here. You can see it's just spinning around. We have the annual revolution as it's going around the sun, and we have this axial precession, which is like wobbling from side to side. So these are the different things that Nicolaus Copernicus was studying, and he figured out the Earth is not at the center of the solar system, but rather it's the sun. The sun is at the center. And he thought that the inner planets are faster and the outer planets are slower. That's interesting theories. So let's see what happens. A little bit later, we get into symbolic algebra. And these kinds of people, Francois Viette and Rene Descartes, they came up with these two books, The Art of Analysis, where Francois finally started writing real equations. I think you could sort of see something like that here. You know, this is mainly just more geometry and some letters being used here, but you know, you can kind of see some equations popping up a little bit here. This is kind of the stuff. This is mainly from La Géométrie from Rene Descartes, but he was using unknowns like x, y, and z, and some constants a, b, and c. He came up with superscripts, and so we finally have the first equations like a plus b equals c, and that was around 1600 or so. Symbolic algebra, finally. And then we have Johannes Kepler, and he created essentially the first laws of physics in physics equation form here. Um, so, I mean, clearly the laws of physics had sort of been maybe started earlier than him, but he wrote the first equations that we have. So we got these, you know, R equals A with a whole bunch of nonsense here. dA over dt equals constant. T squared is proportional to A to the third. So basically these three laws right here. You get elliptical orbits where we have these particular radii, focus points, I suppose. And then there's this elliptical orbit rather than the circular orbit. And the equal areas in equal times, so something like this. You could sweep out a little area like this, which is the same area as this little corner here. You just sweeping that out. It takes the same amount of time to do this than as it does to do this. So this is equal areas and equal times. And we have the harmonic law, which is essentially saying something like the time it takes to go around is like this a to the third. Um, square root of a to the third. So this is the time that it would take to go around the elliptical orbit. And these are his three laws, Kepler's laws, most primitive laws of physics with equations. Johannes Kepler in 1619. The next important person was Galileo Galilei, a few years later in 1638, and he finally came up with the kinematic equations. These are the equations we use today to figure out motion. This is just Galilean relativity, essentially. And so it's basic mechanics, and you can see how he was calculating these things and trying to figure out the gravitational acceleration. So he did that. And then he was also figured out some observational evidence of heliocentrism that, you know, that the sun really does, that it's really not, um, that stuff doesn't just orbit around the Earth. It orbits around other things too. And so he essentially saw that there were moons orbiting around Jupiter instead of around Earth. So he was able to sort of track the motion of these planets around Jupiter, and he saw that they would all sort of remain very close to Jupiter and sort of zigzag from side to side. So that was some observational evidence that Moons orbit Jupiter instead of Earth. Things are orbiting other things. And so that gives sort of more proof that maybe it's not this Earth at the center, but rather maybe it's the Sun that's at the center. So this was Galileo Galilei and some of his contributions. Later we have Rene Descartes. It's up again. He already did some stuff with syncopated algebra, but now he comes back and he has a more important book, or a very strange gravitational theory book. It's kind of another idea, Principia Philosophiae, where he thinks that space is filled with matter, there's no vacuum. He thinks that motion is caused by contact pushing. There's no forces. He thought that orbits were caused by these swirling vortices like this. He didn't have any equations, so he just drew this type of stuff where there's like this like these pockets of different vortices in space that are kind of pushing up against each other and they're causing these other vortex slants, and so things kind of like orbit around the slanted vortexes. This is some crazy stuff by Rene Descartes. A little later we have 1660, Robert Hooke, this little guy right here, and he comes up with this restoring force law. He's looking at springs and he realizes that F equals negative kx. And so, here's this little model here. And he was exchanging letters with Isaac Newton because from this idea that force is proportional to distance, spring force at least, he thought maybe that gravitational force is also um, related to distance. So planetary attraction increases with proximity. He had this sort of a general idea that force is somehow related to distance. So he was giving some ideas to Isaac Newton, which was helpful. But people never really figured out why gravity really was happening, why things were falling towards the Earth, why things were being attracted. So Fatio de Duillier comes up in 1690, a little after Robert Hooke. He's like, well, maybe space is filled with tiny particles like corpuscles, and he's into corpuscles. These are his notes. And maybe objects are bombarded by corpuscles. And maybe there's a shadow pressure that pushes objects around. And this would give a mathematical explanation for gravity. But there was no equations and he never really published this stuff, so it was just some ideas that he had. This was Fatio de Duillier in 1690. And remember that these ideas that sometimes people have, they may not be correct, but they lead to math. And math is good because, you could start to develop math that explains certain things, and then maybe it doesn't really work physically, but later you can use that same math to describe something that's actually physical, maybe in a different context. So you can use mathematics that you build from these very strange ideas, like the shadow pressure pushes objects. A little bit later, this guy, Georges Louis de Lesage, 1784, I think that was 100 years later, he finds these notes on shadow pressure theory. And he's like, you know what? Let me just make some math around that. And so he comes up with this pressure formula and he thinks that the force is, well, he was trying to recreate sort of Newton's laws because Newton had already sort of presented his ideas at this point, but he was trying to recreate that. So F is 1 over R squared somehow. He was trying to prove that there's this shadow pressure that's pushing things around, and that's what's causing the force of gravity. The force is being shielded by the flux. Here are the flux lines, and here are the different things that are blocking the flux and pushing things around. These flux lines, man. This is what his notes was all about. This was Georges Louis Lesage's theory. Shadow pressure. Man, this is some wild, but you know, this is it reminds me of the vents, the circular vents in the sky. How, there's like this blocking type of thing that you can shine through the vent. Well, here maybe it's the opposite because now you're kind of blocking it and then you're shining around it. So these types of mathematics, they're like, why is it that we're coming to these conclusions for gravity? That things are being pushed in a sort of flux way? Because, hmm, Why isn't it the internal part? Why is it only the boundary that's affected by these fluxes? The boundary in the holographic principle becomes much more important later on. But for now, we have these strange theories that shadow pressure is pushing things around. And later on, we get into the precise era where there's revolutionary math and real physics. All these people who we've seen so far, back from Archimedes, these guys were just nearly accurate. So they just had a little bit more advanced math. Their physics was incomplete. We have some good ideas. We have correcting things. We have some modern day patterns that we're still using and some still ideas, but they're very, very incomplete. It's just not even 100% accurate. It's more like approximations. This one's a pretty good one. F equals negative kx. But the shadow pressure stuff is a little crazy.